Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about solubility. So solubility is really going to be examining the behavior of a solid when I place it into water. So how will the solid dissolve, and if so, exactly how much? And because we're going to be using our solubility products in this case, really one of the big things we're going to be needing to do is make sure we have a metric of solubility, which is going to be in concentration units, because that's really where equilibrium constants work the best. So we're going to define solubility as the amount of solid that will dissolve in 1 liter of solvent. So if I have 1 liter of water, what mass or moles of calcium carbonate will dissolve? So as a result, not too surprising, we're going to define our solubilities in 2 key ways. So the first is going to be molar solubilities. So this will be the number of moles that will dissolve in 1 liter. And we'll have beautiful units of molarity, which means it works very well with equilibrium constants, because that will be exactly the units we're looking for. However, it is also worth noting that a much more commonly used metric of solubility is going to be mass solubility, as this can be a little bit easier to measure, where it's literally going to be what mass of a solid will dissolve if I put it in 1 liter. Now, one of the things to watch out here is that this can either be in grams, milligrams, or less frequently, something like micro or nanograms. And again, the choice of mass will likely depend heavily upon exactly how soluble the substance is. The less soluble, the less mass, the smaller the unit you'll use. Now, one of the other things you should watch out for is that both of these metrics have the same constant. They're both described with the variable s. So you'll have to be looking out for what are the units that you're looking for your answer in, or is there a specific request for molar or mass solubility. Regardless, you start solving both these problems the same way. You use an ice table to figure out the molar solubility, and then if you need the mass solubility, you can convert from moles to grams using the molecular weight. So let's go ahead and dive in. So let's go ahead and look at our good old friend calcium carbonate, limestone, quite an abundant substance. Let's try and figure out exactly how much of it would dissolve in a liter of water. So the first thing we're going to want to do is set up our ice table. Now, here we get really lucky because our solids don't show up in ice tables. And we're going to assume that the water's pure, so we shouldn't have any calcium or carbonate already present in the system. In this case, then we just know that we're going to be generating equal amounts of calcium and carbonate. So our equilibrium concentration should be X for both. I can then pair this into my equilibrium constant. So using the value of using the variable X for both the calcium and the carbonate concentration, I know that my equilibrium constant, or my KSP, will just be equal to X squared. So backing this out, take the square root of the KSP value, and we have our X for this reaction. Now what we can do is make use of the fact that since I'm looking for molar solubility, this would be the number of moles of calcium carbonate that would dissolve in 1 liter. Well, it turns out, because of how the stoichiometry works, if I was going to consume calcium carbonate, I would have a minus X here. So it turns out that that the molar solubility will be the same thing as our X value, as long as there's no coefficient in front of your solid. So as long as you make sure that's the case, you solve for X, you solve for S. So our molar solubility is about 5.3 times 10 to the negative fifth. Yeah, this isn't exactly the most soluble of solids. However, let's go ahead and turn that into a mass solubility. So using our molecular weight of 100 grams, we'd find out that the mass solubility will be about 5.3 times 10 to the negative third, or about 5 milligrams. And it is worth noting, there's a lot of limestone out there, and a lot of water running over it. So it is worth noting this is how caves are made, eroding 5 milligrams of limestone at a time until you slowly erode away a cave. Or if there's leftover water, this is how you get stalactites and stalagmites as you're slowly precipitating it out. So again, it's a fairly small value, but it's enough to get real work done over a long term. Now let's go ahead and compare this to another solid, fluoride. So again, it's a little bit lighter at 78 grams, and also worth noting has a slightly lower KSP value. But one of the cool things about fluoride is that it breaks apart into 3 ions, which is going to change our ice table a little bit. Because now instead of generating calcium and 1 ion, we generate 2 anions. So 2 fluorides, which means that when I look at the change, I've got a 2x over here. Woo! Which means that when I'm finding my equilibrium concentrations, I'll have twice as much fluoride as I do calcium, because again, there's more fluoride molecules in the system. However, this gets really fun when we start plugging those equilibrium values back into our KSP equation, because we then have to square that 2x. So it turns out that our KSP equation for fluoride isn't just a simple x squared, it's 4 to the x cubed. Ooh, this gets a little fun because when I have to undo it, we have to divide our KSP value by 4 and then take the cubic root. Watch out for order of operations. Also, if you're working with a calculator system that doesn't do cubic roots, this is the same as raising it to the 1/3 power. So when we do this, we find out that our x and thus our s are going to be about 1.8 times 10 to the negative 4th molar. So again, making use of the fact that we have a stoichiometry of 1 in front of our fluoride. So there's our solubility. However, we can go ahead and multiply this by our molecular weight to get a mass solubility of about 14.4 milligrams per liter. Now let's go ahead and contrast that to our calcium carbonate, because you may notice that something interesting happened here. Calcium carbonate has a lower KSP value, or has a larger KSP value, but a lower solubility. So looking at KSP alone, we would expect the calcium carbonate to have a higher solubility, but instead it has a lower. So one of the things you have to watch out for is the role of stoichiometry. If you break into more components, that will artificially lower your KSP. So in general, as your KSP increases, so will your solubility. But watch out, because if you decompose into more than one component, that solubility gets spread out over each species. So if you have 2 substances with similar KSP values, the one that's more soluble will be the one that breaks apart into more components. So that is one of those things to keep an eye out for. And one of the reasons why it's hard to evaluate solubility by KSP alone, and thus it's very important to be able to calculate your mass and molar solubilities. And because mass solubility is so easily relatable to the general world, it's often used to evaluate a number of properties of a solid, namely its general solubility. So last semester, you may remember we talked about what's a soluble versus an insoluble solid. So our good general solubility rules and tables. Well, it turns out that they were categorized based on these measured solubilities and thrown into 3 general categories. A substance is considered readily soluble, and again, is unlikely to form a solid in water if its solubility is more than 0.1 gram per liter. Now, it is worth noting that this means that there are plenty of substances that are considered soluble that if I throw a single gram of it in a liter of water, not all of it will dissolve. So do keep an eye out for how low this general solubility cutoff is. Similarly, slightly soluble substances go somewhere in between about 0.1 gram per liter and about 1 milligram per liter. So again, according to this rule, both of the substances, calcium carbonate and calcium fluoride we looked at, would be sitting on the very bottom end of slightly soluble. And an insoluble substance is going to be anything that has a solubility less than 1 milligram per liter. And so these are going to be fairly unlikely to stay in solution and will almost always form and precipitate. However, I do want to make note that these are general cutoffs, and there's many substances that sit right around these cutoffs that we move into one category or another. For example, it is very you'll very frequently have fluorite and calcium carbonate labeled as insoluble because they're very near that 1 milligram line. Additionally, it is worth noting there's many substances that are considered soluble that we really do need to keep an eye out for their solubility because there will be a fair bit of it that may end up precipitating. On the other hand, there are plenty of substances that we're going to look at that even though they are considered insoluble, that small amount of ions that they release turns out can have a big impact. This is most prevalent with a lot of environmental contaminants like mercury and lead, where even very small amounts can be quite dangerous. So next time, we're going to go ahead and look at ways we can modify the solubility using the common ion effect. Until then, take care.